Hi there, welcome to lecture 14 of Fox. We're going to talk about advanced counting techniques. So, last time we talked about counting complex objects. The basic idea is think of a complex object as being built up by a sequence of instructions. And if you can count the number of ways to put together that sequence of instructions, you can count the number of complex objects. Okay, we talked about certain rules, the sum and product rule, very powerful rules for counting, and everything we did ultimately boils down to the sum and product rules. We talked about build-up counting, where you build up to a complex problem by solving simpler counting problems. We talked about bijection counting, or one-to-one correspondence, where you can count one set by counting another set if you can establish a correspondence between those two sets. Okay, we ended with the infamous permutations and combinations, and that's related to the number of n-bit sequences with k ones. So n choose k. We introduced this quantity n choose k. It's the number of n-bit sequences with k ones. It's also the number of ways to choose a subset of size k from a set of n objects. And if you still had energy after that, and were able to absorb the binomial theorem, we gave a very nice, cute counting proof of the binomial theorem. Okay, now today we're going to go a little further. We're going to discuss sequences and anagrams. So counting sequences can get a little complicated when you allow repetition. We'll extend the sum rule to this principle of inclusion and exclusion, and with that you have a very powerful counting technique. Okay, the sum rule only holds when you're counting the union of sets that are disjoint, and we can extend it. Inclusion-exclusion holds when the sets can overlap. And lastly, this very interesting principle, very simple but very powerful principle called the Pigeonhole Principle. Pay attention here, because we will ultimately use the Pigeonhole Principle to show that some models of computing, some types of computers are not that powerful. By using the Pigeonhole Principle to identify deficiencies in those models of computing, those computers. Okay. And we'll see some applications of the Pigeonhole Principle. In particular, if you go back to the $100 challenge problem, back then when I showed you the problem, the first thing that should have struck you is, well, maybe this guy's offering $100, maybe the problem cannot be solved. So today, I'm going to show you a very beautiful proof technique. I'm going to prove to you that problem, the $100 subset sum problem, I'm going to prove to you that problem can be solved. Okay? But the way I'm going to prove it to you is going to be quite stunning, in the sense that I'm going to prove to you that it can be solved without giving you any idea whatsoever what the solution is. So hopefully that'll give you renewed motivation to try and solve the problem, because now you know it's solvable. I'm not sending you on a wild goose chase. Okay, let's get started and let's move to the board. Okay, so we had a lot to take in from last lecture on counting, various counting tools. So let's relax today and do some more advanced stuff. Okay, and we're going to talk about anagrams, or sequences with repetition. We're going to talk about overlapping sets, or inclusion-exclusion. And lastly, we're going to talk about this very important principle. It's a simple principle called the pigeonhole. It's going to be very important for us when we talk about the theory of computing, but it's important on its own, especially for counting. Okay, so let's begin. You have, a sequence of letters, Mark, M-A-R-K. Okay, so question. How many words can we get by arranging these letters in various different ways? Okay, so by reordering these letters, by choosing an arrangement of these letters, well, you can think I'm interested in the words. So W1, W2, W3, W4. And this is like, I have 4 students whose first initials are M, A, R, and K. Okay, and I run a race, and how many orders are there for this race to finish? Okay, and so we know how to do this. There are 4 ways to pick the first letter, then 3 ways to pick the second, then 2, then 1, and the product rule says multiply. So this is 4 factorial equals 24. So Mark, number of different permutations of the letters is 24. Okay, let's introduce a complication. And this complication arises if we have some repeated letters. Okay, so let's talk about Anna. Okay, again, I'm interested in rearranging these letters. And, for example, 2 of the rearrangements of Mark are M-A-R-K, and, if I flip, the two of the words that I can make are Mark, and if I flip, I get K-A-R-M, carb. Okay, and these are different words. Okay, and these 2 contribute to this 24, this 4 factorial. Okay, now if I do the same thing with Anna, okay, then I get A-N-N-A, so that's just like Mark, and now I flip the equivalent of the M and the K's, which happen to be the two A's, and I get A, N, and A, and that's the same word. Okay, and this is the complication with counting the number of ways to rearrange, to sort of combine the letters of Anna to get words. Okay, Mark is easy, it's 4 factorial. Anna, if you try to combine, it's going to be much less than 4 factorial, and I leave it as an exercise for you to figure out how many different words can you get. I'll give you a couple of seconds. If you pause the video, and if you're coming back, I need you to verify that there are only 6. Far fewer. Okay, turns out it's 24 divided by 2 divided by 2. If I were to be more, sort of accurate, it's 24 divided by 2 factorial divided by 2 factorial. Okay, and so markedly less, much less, and that has to do with the repetition. So we see that, when sequences have repetitions, okay, counting the number of ways to rearrange and get distinct, sequences, or in the case of words, distinct anagrams, is a little complicated. So let's, try to solve this problem systematically, okay, and let's move up a notch in complexity and consider aardvark. A-A-R-D-V-A-R-K, okay, and we are interested in the number of ways to arrange the letters of aardvark to get different words, okay, and just like Anna, there's repetition, okay, so it's complicated. Okay, so let's sort of break this problem step by step. Okay, and the first thing I'm going to observe is basically what we're interested in is sequence of letters. Okay, so a sequence of 8 letters where, if I count up the number of A's, there are A's, there are R's, so there's A's, 3, there are R's, 2, there's D, there's V, and there's K. Okay, so 1, 1, 1. So how many sequences of, basically what I'm asking is how many sequences of 8 letters are there, okay, where I'm required to place 3 A's, 2 R's, 1 D, 1 V, and 1 K. That's effectively the question that we are asking. Okay, so, if I were to generalize this question, I could think of the A as a type of object, the R as a type of object, the D, V, and K as types of objects. They happen to be different letters. Okay, and I'm asking for a sequence of length 8, okay, in which there are 3 of type 1, 2 of type 2, 1, 1, 1 of types 3, 4, and 5. So I have different types of objects, okay, and I'm interested in a sequence in which I'm required to place a certain number of each type of objects. So if I were to further generalize, I could introduce the concept of an N sequence. So the length of the sequence is N, in this case 8. Okay, and I have different types of objects. In this case, there are 5 objects. So imagine I have R types of objects, and I want K1. So in this case, 3 of type 1. Okay, 3 A's. K1 of type 1. Okay, 2 of type 2. 2 R's. K2 of type 2. And so on. K sub R of type R. Okay, so the most general version of this problem is to say I'm interested in a sequence of length n, okay, and I have R types of objects, and you're required to place K1 of type 1 in my sequence, K2 of type 2, up to KR of type R. Okay, since it's an n sequence and this is the number of each type, it had better be the case that K1 plus K2 plus KR must equal n. So sometimes we will call this a K1, K2, K3, ... K sub R sequence. Okay, and the number of ways of doing that, we will write as N, K1, K2, K3, KR. Okay, and so here we are interested in 8. We are interested in 8. 3, 2, 1, 1, 1. So we have a sequence of length 8, okay, with 3 objects of type 1, 2 objects of type 2, 1 object of type 3, 1 of type 4, 1 of type 5. Okay, so this is just sort of introducing a general notation, okay, and I just want to illustrate with anagrams that constructing anagrams is a special case of this general type of problem. So let's go ahead and solve this problem in a systematic way, and the way we solve the problem, it'll become obvious what the solution is what the answer is to the general problem. How many ways are there, to construct a sequence of n objects with certain specified numbers of each type. Okay, and then we'll summarize, okay, and do some applications. So effectively, I'm looking for a sequence of length 8 with some letters. Okay, so let's create some boxes where I'm going to put the letters in a sequence of length 8. So here's my sequence of length 8. Okay, and I'm going to create 8 boxes. Okay, in which I'm going to place the letters, and I have to place this distribution of letters, and then I will have a rearrangement of the or an arrangement of the letters in aardvark to form some other weird word, perhaps. And I'm interested in how many ways can I do that. So since I have to place all of these letters, okay, I might as well start with the A's. Okay, so step 1, start with A's, and more generally start with type 1. Okay, so start with the A's, and okay, now, what about the A's will make, a word different. So effectively, I need to place the A's in 3 of these slots. And if I place them in 3 slots, in three slots, or if I change the 3 slots, I've changed the word. Okay? But with respect to the A's, the only thing that matters is which slots do the A's go into. For example, I might pick this slot, and this slot. Okay? And put A's here. A. Okay? So, in my first step, where I start with the A's, I have to choose 3 of the boxes out of the total of 8 boxes in which to place the A's. Okay? So, there are 8 choose 3 ways of doing that, because I'm choosing a subset of size 3 from 8. Okay? And we solved that problem last time when we talked about combinations and permutations. Okay? So, the number of ways to place, so place 3 A's, okay, i.e. choose 3 boxes from 8. And the number of ways to do this is 8 choose 3. Okay, that, we talked about last time. The number of ways to choose k boxes, number of ways to choose k objects out of a set of n. The number of k subsets from a set of size n. In this case, k is 3, n is 8. Okay, now I'm thinking of, the product rule, which we talked about last time, where, if I said that, so if there are n1 ways of doing x1, and after you have done x1, if there are n2 ways of doing x2, okay, and so on and so forth, then the total number of ways of doing whatever you're trying to do, for example, construct this sequence of steps x1, x2 up to x, k, is the product of the number of ways. But providing that after you do x1, you fix what you did for x1 and consider the number of ways to do x2 after you have fixed x1. Okay? So what's my next step here? My next step here is place 2 R's. Okay, but after I have placed the A's. Now, okay, how do I place the 2 R's after I place the A's? Well, the A's occupy 3 of these boxes. Okay, so in order to place the R's, I have to choose 2 of the remaining boxes that are left vacant after I place the A's. So I have to choose 2 of the boxes from the remaining 5. Choose 2 boxes from 5. Okay. And so how many ways can I do that? I can do that in 5 choose 2 ways. That's what we solved last time. Okay, now I can go more quickly. 3. So now, let's say I place the R's, I'll place the R's, I don't know, here and here. Okay, so I chose those 2 boxes out of the remaining 5. How many boxes remain? 3. So place 1D. So choose 1 box from 3. So how many ways can I do that? 3 choose 1. Okay, and then, so suppose I place the D here, D. Okay, and then 4, place 1V, so choose 1 box from how many? From 2. From 2, i.e. there are 2 choose 1 ways of doing this. Okay, so where will I place the V? Maybe here, I don't know. Okay, and Step 5, place 1k. So choose one box from how many boxes remain? 1. Okay, and that's not really a choice. It's not much of a choice, but nevertheless, we can do it in choose one ways. Okay, and at the end of the day, I've placed my k here, and I've constructed the word Vadraka, whatever. Okay. All right. So, what have I accomplished? I have systematically, in 5 steps, okay, constructed an arrangement of the words. Okay. And my first step had this many ways, my second step had this many ways after doing the first step, my third step had this many ways after doing the first 2, okay, and my fourth had this many ways after doing the first 3, and my fifth had this many ways after doing the first 4. Okay. So the product rule says number of ways is the product 8, 3 times 5, 2 times 3, 1 times 2, 1 times 1, 1. Okay. Wow, very complicated. Yes, very complicated. Okay, so there's the answer. Okay, that's the number of ways of choosing the A's, then the V's, then the R's, then the D's, then the V's, then the K's. And so that's the number of anagrams for these letters. Okay. And so we've solved the problem of counting sequences with repetition. But let's simplify. Okay. Observe that this is 8 factorial over 3 factorial times 5 factorial. So we gave the formula before. So let me write that important formula again. So n choose k is n factorial over k factorial times n minus k factorial. Okay. So this is 8 choose 3 times 5 choose 2. So that's 5 factorial over 2 factorial, 3 factorial. And then 3 choose 1 is 3 factorial divided by 1 factorial, 2 factorial. So 1 factorial, 3 minus 1 factorial. Times 2 factorial over 1 factorial, 1 factorial. Times 1 factorial over 1 factorial, 0 factorial. And you need to know that 0 factorial is 1. Okay, and that looks even more complicated. I said I'm going to simplify, but yes, because, look, there's a lot of cancellation that takes place. So this 5 factorial cancels with that 5 factorial. This 3 factorial cancels with this 3 factorial. And you see this continues. Okay, this 2 factorial cancels with this 2 factorial. Okay, and this 1 factorial cancels with this 1 factorial. Okay, 1, 1. The 1 it's kind of trivial to cancel out 1s. Okay, so what do we, and 0 factorial is always 1, so we can ignore that. Okay, so what do we end up with? We end up with 8 factorial divided by 3 factorial, 2 factorial, 1 factorial, 1 factorial, 1 factorial. Much simpler. Okay, and now let's do some pattern recognition. Effectively what we have proved, and now you can see the formal proofs in the text, and of this important formula, we even give 2 different proofs. One based on, sort of a bijection approach using multiplicity, and the other, which is just this approach, but generalized to the general case. Okay, but what you will observe is that 8, where did we see 8 before? 8. It's the number of letters total. It's the length of the sequence. So 8 is n. Where did we see 3? 3, 2, 2. 1, 1, 1, 1, 1, 1. And if you do this for the general case, you will get exactly the same formula, but instead it will be, in the general case, it will be n factorial, so n factorial, 8 factorial, divided by k1 factorial, k2 factorial, all the way to k sub r factorial. Okay. And there's another way to see this, is that you can take all the 8 factorial ways of arranging the words, treating them as the letters, treating them as all distinct. But now once you have arranged the A's, okay, there are 3 factorial ways of permuting the A's, which give you the same word. So we have to divide out that 3 factorial. And there are 2 factorial ways of permuting the r's, which give you the same word. So you have to divide out that 2 factorial. Now that's related to multiplicity-based, correspondences and counting using those. And you can read about that a little in the previous chapter. Okay. But basically we've proved this formula. And it's a very powerful formula. Okay. So let me show you a couple of applications. Well, let's first do an example. If we wanted to solve the problem for aardvark, well, you just need to compute that number. Okay. Example. So, you're going to have a parade, and you have a road, okay, and you have black flags, 3 of them, and blue flags, 3 of them, and red flags, 3 of them. This is the way I draw flags. Okay. And then the question becomes, well, I'd like to figure out, how many ways are there, how many distinct ways are there for me to sort of arrange these flags in a row on the street, okay? And so that, every time I have the parade, I'll have a different arrangement of the flags. Okay. Well, I have a sequence of 9 objects. So n equals 9, okay? And 3 of type 1. What is type 1? Black. Okay. 3 of type 1, so K1 equals 3. 3 of type 2, so 3 of type 2, so K2 equals 3. 3 of type 3, so K3 equals 3. So the number of rearrangements, so the number of sequences where I have this kind of repetition, okay, is just the total number of objects, 9 factorial over 3 factorial, 3 factorial, 3 factorial. Done. Binary sequences. Okay. So a binary sequence of length n with k ones. We saw before that this was n choose k, okay? But now I'm going to think about it this way. I have n objects, so n objects. K are 1. You can think of this as type 1. Okay? And there's a second kind of object. So we have only 2 objects if it's a binary sequence. And how many are type 2? N minus k are type 2. These are zeros, are 0, which is type 2. So, using this formula, the number of distinct sequences where I have 2 types of objects, k of type 1 and n minus k of type 2 is n factorial divided by k factorial, okay, divided by each of these factorial, n minus k factorial, and lo and behold, ta-da, same formula. Good thing that, things derived in different ways agree, okay? And so, in effect, n choose k, nk is a shorthand notation for nk, n minus k. So in this notation, we would write nk as n, type 1 k, type 2 n minus k. So you have k1 and k2. But we just shorten that to nk. Because if you know n and k, you know n minus k. Okay, one final application. Okay, let's consider the trinomial. The trinomial. Okay, so x plus y plus z to the power n. Okay, so, if you expand this, it's x plus y plus z, x plus y plus z, x plus y plus z. Okay, a bunch of x plus y plus z's. There are n of them. So you'll generate an n sequence. You'll generate n sequences with x's, y's, and z's. Okay, and so we may ask how many such sequences will you generate? Okay, you'll generate 3 to the n, 3 times 3 times 3 times 3, depending on which one you pick from here and here and here and so on. Okay, so 3 to the n such sequences, and when you collect up terms, some of them will have I x's, some of them will have j y's, and some of them will have n minus I minus j z's. So the powers of x, y, and z that will appear are of the form x to the I, y to the j, and then z to the n minus I minus j. Okay, so this is a typical monomial that will appear in this expansion. And we might ask, if I tell you I, j, and n minus I minus j, okay, so let's call this k. If I tell you I, j, and k, so if I tell you, and it must be the case that I plus j plus k is equal to n. Okay. If I tell you I, j, and k, I can ask, what's the coefficient of that monomial? Well, it's the number of sequences with I x's, j y's, and z k's. That's just n factorial divided by I factorial, j factorial, k factorial. Okay. N factorial divided by the product of these three factorials. That's this formula. Okay. And so this guy is the sum over all I plus j plus k equals to n of terms of this form. And the coefficient of x to the I, y to the j, z to the k is, n factorial divided by I factorial, j factorial, k factorial. This, okay, that this equates to sums of terms of this form is an example of what's called the multinomial theorem. And the special case of that is the binomial theorem, which we discussed last time. Okay, let me give you a cheat sheet. Much as I hate cheat sheets, it's worth having this cheat sheet. Okay, okay, so a cheat sheet for certain counting problems, and we're going to break the counting problems. So sequences, we're building up different sequences. We're going to break them up into with repetition and without repetition. So with repetition and without repetition. Okay, and then we're going to be interested in sequences. Okay, so sequence, so a k sequence and a k subset. So with repetition, without repetition, we've been discussing repetition so far. A sequence means that the order matters, and a subset means that you don't care about the order. So in all cases, think about it as we have n objects. Okay, and we're interested in constructing a sequence of length k. Okay, and if it's with repetition, okay, then each element of my sequence can be one of the n objects. So the number of ways to do it is n raised to the power k. Okay. If it's without repetition, think of this as you have n runners in the race, and I have to select k for the top k finishers. So without repetition, it's going to be n times n minus 1 times n minus 2 all the way down until I have all my k objects. So this is going to be n factorial over n minus k factorial. Okay. So constructing these sequences. So a k sequence with repetition from n objects, without repetition from n objects. Okay. Now, if it's a subset, the order doesn't matter. Okay. So if we do with repetition, so if we're picking a subset and we're allowed to repeat the objects, then it's exactly the goodie bags. Okay. So it's exactly the goodie bags where my goodie bag has k. Okay. And I have n types of colors, n types of candy, let's say, and I'm allowed to repeat colors. Okay. And we saw before that, it's k plus n minus 1, choose n minus 1. We developed this formula last time using correspondence-based counting. Now, if it's without repetition and it's a k subset, so the number of ways to choose k objects from n objects without repetition, in other words, without replacement. Okay, so then this would be n choose k, choosing k objects from n without repetition, so without replacement. Okay, so that's a nice cheat sheet to have. And we have one more thing here, which is, you can think of this as the K1, K2, K3 up to K sub R sequence. Okay. And now here we're explicitly sort of allowing repetition. This is what we just described and what we just discussed with anagrams and so on and so forth. And so this will be the total number of objects that you're building your sequence for. Okay, so K1 plus K2 plus up to plus K sub R. So we'll list it under with repetition, or divided by, so factorial, divided by K1 factorial, K2 factorial, dot, 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 K sub R factorial. And, okay, so that's just a useful cheat sheet for counting. So try to identify, am I interested in a sequence? Does order matter? Or am I interested in a subset? Order doesn't matter. Okay, it's just, I'm just picking a collection of items. Am I allowed to repeat items? Am I not allowed to repeat items? And this is sort of, the case we studied today, where I have a sequence. So it is a sequence, but it's not of length k. It's of length the sum of these, and I'm required to pick a certain number of elements of each type. Okay, so let's erase, and we're going to come back and talk about overlapping sets and inclusion-exclusion, and then we'll talk about the pigeonhole principle. I'm going to erase everything. Bam! Okay, so let's now generalize the sum rule. So this more general version of the sum rule is sometimes called the principle of inclusion-exclusion. Okay, big words. Basically what it means is how to compute, the number of objects when, previously we said that if you have n objects and there are n1 of type 1 and n2 of type 2, okay, then the total number of objects n is equal to n1 plus n2. Okay, so sum rule, so inclusion, exclusion. So you have two sets of objects, and there's n1 here, n2, and so the total number n is n1 plus n2. Okay, and that relies on the fact, that each object is either n1 or it's n2, but it cannot be both types. Okay, so it's sort of like you're one of those types. Okay, and then I can count up type 1, count up type 2, add them together, I get the total number of objects. Okay, the situation is different if the types can overlap. Okay, so let's look at two overlapping sets. Okay, so basically this says that, the union A1 union A2, when they're disjoint, is equal to the sum of the two sizes. Okay? Now, things get complicated if these two sets can overlap. And, the number of biology books are, 500, and the number of statistics books are, 300. So how many books in all? Well, we might think it's 500 plus 300. But in that example, you've got biology books. Okay, and you've got statistics books. And you have some biostatistics books. Okay, so there's overlap. So you cannot just add. So let's see what's the size of this union. So this union is made up of three regions. And let me color code these three regions. So there's the biology books, which I'm going to color code with, black. And then there's the, statistics books. Let me color code those blue. There's this region. Okay, so think of this as biology only, statistics only. And then there are the joint books, the biostatistics books. Okay, so let's color this region red. Now, we're interested in the size of this whole region, the size of the union, or the number of elements in the union. Okay, so the union, union is equal to black plus red plus blue. Now that I can do because look, the black, the red, and the blue are disjoint regions. So I can apply the sum rule to black, red, and blue. Okay. But we can say biology is equal to black plus red. And statistics is equal to blue plus red. Okay, now I would like to take, and we know that the number of books in biology is 500, and the number of books in statistics is 300. Okay, and I would like to take the sum of these. So bio plus stat, so bio plus statistic is black plus red. So it's black plus red plus blue plus red. So black plus red plus blue plus red. Okay, and if we compare that to the size of the union, we see that the union is black plus red plus blue, black plus red plus blue. So I have an extra red in here when I just add bio and statistics. Okay? So I have to subtract the red. And that'll get rid of this red, and now I have black plus red plus blue, which is indeed the size of the union. Okay. Now, let me write that in a more general setting where, we can think of this set as A, this set as B, and we're interested in the union, or A1, A2. So we're interested in the union of A1 union A2. Okay. And I want, A1, so this is bio, plus A2. So this is size of A1 plus the size of A2. But now that adds the red region twice, so I need to subtract the red region. But what is the red region? The red region is just the intersection, minus A1 intersection A2. So, as stated, the problem cannot be solved. How many books in all? I would like to take 500 plus 300, which is 800. But now I need to subtract the red region once, so I need to know how many books are in both bio and statistics. I need to know the number of biostat books. Okay. Actually, this is a special case of this, where the intersection is 0. So this is more general. Now you might think, well, this was nice and convenient for using the counting, for using the sum rule for counting, because if I can count n1 objects in set 1 and n2 objects in set 2, then I can just add. So basically the sum rule allows us to simplify the counting of a complex object by breaking it down into simpler types and counting each type. And this is similar in spirit. It allows us to count the complex objects, which is this whole set, by breaking it down into 3 types of sets. These sets, those which are only biology, those which are biology, those which are statistics. But now I also need to count one more set, which is those which are both biology and statistics. Okay? And you might ask, why is that any easier than counting those which are biology or statistics? So this is biology or statistics, biology and statistics. Often it's easier to count the and, the intersection, than it is to count the or. And so that's why this is useful, because count the first type, count the second type, and then count those that are both types. Okay? So let's do an example. Example. How many numbers in the range from 1, 2, 3, up to 100 are divisible by 2, or divisible by 5. Okay? So, the way we can approach this kind of a problem is to define 2 sets. Let me define the set A2. A2 equals numbers divisible by 2. Okay? So those are just the multiples of 2. So those are the multiples of 2, which is 2, 4, 6, 8, and so on, up to 100. Okay, and we can see that this is exactly, the size of this set is exactly 100 divided by 2. So the multiples of 2 occur every second number. Okay, so it's 100 divided by 2. If I wanted to be more technically correct, I should take the floor. I should round down. Okay, I should round down. Because if I wanted the number of multiples of 2 in the range from 1 to 101, I would do 101 divided by 2, but that sounds like 50.5. No, it's 50. So I should round down. Okay? And I can define A5, which is equal to the multiples of 5, the number of multiples of 5, which is just going to be 100 divided by 5, rounded down, which is 20. Okay? And so I would think that your divisible by 2 or your divisible by 5 might be the sum of these. So this is 50. Okay, so divisible by 2 or divisible by 5 equals, the sum 50 plus 20, except that I would be wrong, because there is an intersection. A2 intersection A5 is the numbers divisible by 2 and 5. Okay, so if you're divisible by 2 and 5, it means that you're divisible by the least common multiple of 2 and 5. Okay, so this is, 100 divided by the LCM of 2 and 5. Okay. The least common multiple. If a number is divisible by both 2 and 5, if and only if it is divisible by the least common multiple, okay, of 2 and 5. And the least common multiple of 2 and 5 is 10. So this is equal to, 100 divided by 10. Sorry, I take the floor. I round it down, which is 10. So I have to subtract the 10. Okay? So minus the intersection. Minus the intersection 10. Okay. Let's do another example. Okay. Okay. Passwords. So remember we talked about counting passwords. There are the 26. There are 26 lowercase characters, 26 upper, 10 digits, and 10 special. And the password has length 8. So password is equal to W1, W2, W3, W8. Okay. And nowadays it's getting even more complicated. So, well, first of all, this gives a total of 72 possible characters, 72 choices for a character. And if you have 8 characters in the password, you can sample, you can repeat characters. So the number of possible passwords, is equal to 72 to the 8. Okay. Now, it's getting complicated. Nowadays, they want you to have both an uppercase letter and a special character. Okay. So, valid passwords. So valid means you have an uppercase letter and a lowercase. And a special. Okay. So let's define the set of passwords that do not have an uppercase letter. So let's call this A sub U is, do not have uppercase. Okay. And A sub S, so the specials, so A sub S is the set of passwords that do not have a special. Right? Then the invalid passwords do not have an uppercase or do not have a special. So invalid. So the invalid passwords are the ones in AU union A sub S. AU union AS. They do not have uppercase or they do not have a special character. So let's compute the number of invalid passwords. Okay. So the number of invalid passwords is equal to the size of AU plus the size of AS minus the size of the intersection. AU intersection AS. And this is an example where counting the intersection is much easier than counting the union. Okay, so the size of this guy is the size of this guy, which is the size of AU plus the size of A sub S minus the intersection. Now, if it doesn't have an uppercase letter, it means it's using 46 of these digits. These 26 plus these 20, so 46. And so you can construct any password you want of length 8 with just 46 choices for each character. So this guy here is 46 to the 8. If it doesn't have a special, it's using all the characters but these 10, so there are 62 choices for each character. So plus 62 raised to the power 8. And now we have to subtract the intersection. So if it doesn't have an uppercase and it doesn't have a special, it means you're not using the uppercase or the specials. Okay, so you're using just the digits and the lowercase in your password. So that's 36 choices for your password of size 8. So you have to subtract 36 to the power 8. Okay, so that's the number of invalid passwords. And why is that useful? That's useful because we have the sum rule that the total number of passwords, is equal to the valid plus the invalid. Okay, and so this here is 72 to the 8 is equal to the valid plus the invalid, which is 46 to the 8 plus 62 to the 8 minus 36 to the 8. Okay, so the number of valid passwords, is equal to 72 to the 8, okay, minus 62 to the 8 minus 46 to the 8 plus 36 to the 8. Okay. So nowadays, it's getting more complicated. They require uppercase and special, and so the number of valid passwords has dropped compared to if you only required a special. Okay. And you can go and compute this number. Straightforward application, well, not straightforward, but an application of the size of a union of overlapping sets. Okay. Now, let's erase and talk about it. What about if you have more than two sets? Okay, so what about the union of three sets? So let's generalize the union of two sets to the union of three sets. So we have three sets, A1, A2, A3, and we're interested in A1, union A2, union A3. So we're interested in the size of the union of three sets. Okay. Now, you could treat this as two sets, where one of the sets is A1 union A2, set 1, and this is the second set, set 2. Okay, so then you can use the union of two sets to write this out, and then, so you can expand this out with the union of two sets, then you can continue the expansion and continue the derivation, and ultimately you'll get a formula for the union of three sets. So I'm going to leave that as an exercise for you, and you can read the textbook, it's in the textbook. So I'm going to give a slightly different derivation, okay, where, what I will observe is I'll do the usual thing. I'll do what I thought I should do in the first place, which is add up the three sizes, okay, which is what I would start off by doing in a naive way. Okay, so it's the size of A1 plus the size of A2 plus the size of A3. Okay, but now, if you think about it, when I added A1, which means I added this intersection, for example, this intersection. I also added the other intersection, but let me focus on the blue intersection. When I added A2, I added that intersection again. So I've added that intersection twice. Okay, and when I added A1 and A3, when I added A1, I added this intersection. And then I added it again when I added A3, and similarly with this intersection. A2 adds it, A3 adds it. So each of these blue intersections has been added twice. So I need to subtract them at least once, okay, or once. So let me subtract A1 intersection A2, A1 intersection A2. I'll subtract A1 intersection A3, so that piece, A1 intersection A3. And I'm subtracting because I added those twice, and I'm subtracting A2 intersection A3. Okay, so I'm subtracting A2 intersection A3. Okay, but now, so that takes care of these blue regions have all been added in exactly once. So these outer regions have been added once from these guys, and now the blue regions have been added exactly once. And so now let's see what's going on with this red region. Okay. When I added A1, A2, and A3, I added the red region once each time. So I've added the red region in 3 times. Okay, and then when I subtracted this intersection and that intersection and that intersection, the 3 intersections, I subtracted the red region 3 times. So I added it 3 times, I subtracted it 3 times. But then it's not there at all. It needs to be there once. Okay, so I need to add it back. So I need to add back A1 intersection A2 intersection A3. Okay, and this formula, which you can derive, okay, more formally, I left it as an exercise, okay, is the formula for the inclusion-exclusion formula for the union of 3 sets. Okay. This pattern generalizes. So add the sets, then subtract the intersections, then add the 3rd intersection. If I had 4 sets, I would add the sets, subtract the 2-way intersection, add the 3-way intersections, and then subtract the 4-way intersection. Okay, and that's the general inclusion-exclusion formula for the sum of, for the union, for the size of the union of n sets. Let me just state it, okay, just so that I have stated it, but you can see the details in the text. So inclusion, exclusion for n sets A1, A2, up to A sub n. Okay, so what you do is you consider all the k-way intersections. So here's the 1-way intersection, it's just the sets. 2-way intersections, 3-way intersections, and so on. So the size of A1, union A2, union AN. So the size of the union of n sets is, you consider all k-way intersections. Okay, and then you either add or subtract or add depending on what the value of k is. And add/subtract depending on k. So you start by adding the one-way intersections, then you subtract the two-way, then you add the three-way, then you subtract the four-way, and so on. So we can write this compactly as the sum from k equals 1 to n. Okay, so you start with the one-way intersections, then the two-way intersections, and so on. Okay, but because of this alternating sign, we need something like -1 to the k. Well, it's actually -1 to the k plus 1. Okay, so the one-way you add, the two-way you subtract, the three-way you add, and so on. Okay, of the sum of sizes of all k-way intersections. Okay, so you get the sizes of all the k-way intersections, the sizes of all the two-way intersections, and then you either add or subtract the sum of all the three-way intersections, and then you add or subtract depending on the sign of -1 to the k plus 1. Okay, so this is the general formula, but we'll work with the three sets for the moment. Okay, and let's do an example. Okay, so three ladies walk up to the coat check in a restaurant. Okay, so you have lady 1, lady 2, lady 3. Okay, and they have their coats. Let's call them coat 1, coat 2, coat 3. Okay, so they check in the coats, and then when they're leaving, they get back the coats. Okay, and we're interested in the situation where none of the ladies get back their correct coat. Okay, so an example of such a situation is for lady 1, I give coat 2. For lady 2, I give coat 3. Okay, for lady 3, I give coat 1. Okay, so this is an example of what we call a derangement. So, none of them get back their same coat. And you could imagine generalizing this problem to n ladies. And that's called a derangement among n objects. So, n objects started out in some order, and now I'm going to mix them up so that no object is in the same place that it was before. It's called a derangement, the opposite of an arrangement. Okay, so we're interested in the number of derangements. How many ways are there for all the ladies to get back the wrong coat? So all ladies get back the wrong coat. How many ways? Okay, we want to count derangements. Now, there's a build-up way to count the derangements, and you can see the text for that. Okay, I'm going to show you the inclusion-exclusion approach to counting the derangements. Okay, so let us define the number of ways in which lady 1 gets back their coat. So let us define A1 equals the number of, orderings where, well, equal to the orderings, let's call it the orderings where lady 1 gets her coat. And let me define A2 as the orderings where lady 2 gets her coat, and A3 as the orderings where lady 3 gets her coat. Okay. So in these orderings, lady 1 gets her coat. In these orderings, lady 2 gets her coat, and in these orderings, lady 3 gets her coat. Okay. And how many orderings in total? Orderings in total, well, the first coat can go to anyone. I mean, the lady 1 can get a coat in 3 ways, then lady 2 can get a coat in 2 ways after lady 1 has picked a coat, and then lady 3 gets the coat that remains. So there are 3 ways for lady 1 to get a coat, and once you fix lady 1's coat, there are 2 ways for lady 2, and then there's 1 way for lady 3. So, there are 3 times 2 times 1 ways in which you can assign the coats. Okay, so that's 6 ways. Or 3 factorial. 3 factorial. Okay, and okay, the ways, the orderings in which at least someone gets their code means that either lady 1 gets her code, or lady 2, or lady 3. So A1 union A2 union A3. Okay, this is the orderings where someone gets her code. Okay, so if we know the size of this, we can subtract it from 6, and we can get the number of ways in which no one gets their code. Okay, so the size of A1 union A2 union A3 is equal to the size of A1 plus the size of A2 plus the size of A3, okay, minus the pairwise intersections, minus the size of A1 intersection A2, minus the size of A1 intersection A3, minus the size of A2 intersection A3, okay, and then plus the size of A1 intersection A2 intersection A3. Okay, so that's the inclusion-exclusion formula for the union of 3 sets. Wow, man. Okay, what's the size of A1? So, lady 1 gets her code. So now, lady 1 gets her code. So this is C1. Okay, and then now there are 2 ways for lady 2 to get her code. So there are 2 ways for lady 2 to get her code, and then 1 way for lady 3 to get the remaining code. So 2 times 1 is 2. So this is 2. And similarly, for the number of ways in which, because by symmetry, there's no difference between lady 1, 2, and 3. So the number of ways in which lady 2 gets her code is also 2. So this is 2, and this is 2. Okay. Now, A1 and A2. If A1 and A2 get their codes, so C1, lady 1 gets code C1, lady 2 gets code C2. Well, that just leaves code C3 for lady 3. So there's only one way in which, A1 and A2 get their code. One way. And similarly, there's only one way for A1 and A3, and there's only one way for A2 and A3. Okay. What about, A1 intersection A2 intersection A3? A1 intersection A2 intersection A3 means lady 1 gets her code, lady 2 gets her code, and lady 3 gets her code. So that's this one ordering. So there's just one way to do this. So the final answer, 6 minus 3 plus 1, which is equal to 6 minus 3 plus 1 is 4. So there are 4 ways, okay, in which someone gets their code. Okay. So the derangements, the ways in which no one gets their code, so the derangements, so this is the number of ways in which no one gets their code, is going to equal 6, the total number of ways to hand out the code, 6, minus the number of ways in which someone gets their code, minus 4, which is equal to 2. Bam! So there are 2 derangements when it comes to 3 objects. Let's see if we can figure them out. Well, so if it's a derangement, then, lady 1 must get either 2 or 3. So if lady 1 gets 2, then, lady 2 being a derangement lady 3 being a derangement cannot get code 3, so must get code 1, and that means that lady 2 must get code 3. Okay. On the other hand, lady 1 could get code 1, in which case, lady 1 could get code 3. Lady 2 cannot get code 2, so code 2 must go here, and therefore that leaves code 1 for lady 2. So C2, C3, C1, and C3, C1, C2 are the only 2 derangements, and that's what we got. Okay. So, inclusion, exclusion. I've now left, lots of time to talk about the pigeonhole principle. What a simple principle, okay? And, it's very powerful. It's just a beautiful principle, just both on the grounds of how simple it is and on the grounds of how many applications it has. Okay? And it's going to be a very powerful application for us when we study the theory of computing, when it comes time to build a digital computer, okay, using all the discrete math that we have learned. Okay, so let's talk about the pigeonhole. Let me erase. And before I talk about the pigeonhole, I want to introduce you to something called a non-constructive proof. So let's do the speed erase. Bam, 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 bam. Non-constructive proof. Okay, so what's the idea? The idea and an example of a non-constructive proof is, can you convince someone, or can you prove to someone that something exists without showing them how to find it, without showing them where it actually is? So that's an example of a non-constructive proof of existence. I'm going to prove to you that something exists without, telling you how to find it. Now, here's an example of non-constructive proof, although you might be wondering, this looks like a kid's picture book. Okay, yes. So, this is an instance of the game called I Spy, and you may also be familiar with a game called Where's Waldo, where you have to find Waldo in a picture. Well, in this instance of I Spy, you have to find this black cat in this picture. Okay, so I gave this puzzle to my 4-year-old, and the 4-year-old looks around for about 10 seconds and says, "Dad, you're just conning me. This is a wild goose chase. You're just trying to waste my time. I don't even know that there's a black cat in this picture." And off he goes, to the playground. Okay. So now, if I really want him to solve this problem, and I don't want him to think that I'm trying to trick him, okay, I need to somehow prove to my 4-year-old that the cat exists in this picture. But then, if I go and show him where it is, then that's then the puzzle is useless. Okay, that defeats the whole purpose. Okay, so think to yourself for a few seconds, how would you prove to a 4-year-old that this black cat exists in this picture? Now you can look around. Trust me, the black cat exists, and now you'll start thinking, really? I don't think it exists. This is a joke. Okay, so I'm going to try to prove to you that the black cat exists. But now think to yourself, how would I do that without giving the game away? That's the challenge. Okay. So here's an idea. At least for this example, just to illustrate to you the concept of a non-constructive proof, because you might be thinking there's no way to prove it to me without actually showing it to me. So here's my idea. I'm going to, cover this picture with a black cloth, a huge infinite black cloth, move the picture all around under it so that you don't know where in the black cloth the picture is. Okay. Now I'm going to take an X-ray lens, okay, and put it on top of the black cloth just above where the cat is. Okay. So it's going to reveal the cat, but in no way reveal the location. Okay. So here, I've attempted to do that. There, look. Now, do you believe me? The black cat exists in this picture. So I've sort of taken this X-ray lens on top of this black cloth and put it right on top of the cat. And, I'm now showing you that the cat exists. So now you know that the cat exists. Okay, but actually the 4-year-old has got the better of me, because look, I've not only revealed the cat, but I've revealed some hints as to, some of the things that are surrounding the cat. So I really need, an X-ray lens that's exactly the shape and size of the cat, so that I can just put it on top of the cat and say, here, look, the cat's there, and I'm not going to show you anything else. And that's a non-constructive proof. So now you can go back and see, can you find the cat? And when you think about it, you think, oh, the cat must be somewhere here, because, that was the proof I gave you. But when you look, oh, it's not there, because I've given you, in some sense, a non-constructive proof that doesn't tell you where the cat is. Okay, so we're going to talk about the pigeonhole principle. And one of the biggest uses of the pigeonhole principle is to show that something exists without in any way, revealing or, in fact, divulging exactly what, or where that thing is. And you might wonder, well, really, is this a useful concept? Well, certainly to show that the cat exists in this picture is useful for me if I'm trying to convince the 4-year-old. But what about in real practice in computer science? Well, yes, it's a very useful concept. Okay, so think about bank security. So you come to the ATM. Okay? You don't know who's behind the ATM. Now, you want to convince the ATM that it's you, okay, so that it'll give you your money. But in convincing the ATM that it's you, you actually want a non-constructive, or sometimes called a zero information proof. I just want to convince the ATM that it's me, and the ATM shouldn't know anything else. In particular, the ATM shouldn't be able to go and convince someone else that they are me and take my money out of some other bank. So in other words, I want to convince you that it's me, but I don't want, you to be able to sort of in any way replicate that, that proof. So I just want you to believe that it's me. Just like I just want you to believe that the cat is there without actually knowing where. Digital signatures. I just want you to know that I signed this document. So I want to prove to you that I signed this document without giving you the ability to sign documents on my behalf. Because if you think about it, in the modern way in the olden days of doing things, you just write your signature on a piece of paper and give it to someone. And they, oh, that's your signature. But now they have your signature. They can replace it. They can replicate it. They can use your signature and sign a check on your behalf and take all your money. So that's not good. These are examples of, in some sense, non-constructive proof. Proving to someone that, something is true without giving them the ability to find it or replicate or something like that. Okay, so let's talk about pigeonhole. All right, the pigeonhole principle. Okay, and the idea is very simple. Okay, so if you have 2 spare rooms in your house and 3 guests come over for the night, at least 2 of the guests are going to have to share a room. Okay, that's the basic idea. That's all there is to it. Okay, so think, pigeonholes. You have, let's say, 9 pigeonholes, and if you have 10 pigeons, P1 up to P10, and I try to place them in the pigeonholes. So, you might place P1, P2, P3, P4, P5, P6, P7, P8, P9. Okay, now where do you place P10? Oh, all the pigeonholes are occupied, so P10 might go here. So P4 and pigeon 4 and pigeon 10 have to share a pigeonhole. And that's the pigeonhole principle, in this example and in general. So let me just state it. And, you can prove this principle by contradiction, and I encourage you to do so. Otherwise, look in the text for the proof. But it's so kind of intuitively obvious that I'm not going to give you the proof here. So if you have pigeons, and pigeonholes. Okay, and the number of pigeons is greater than the number of pigeonholes. So you have more pigeons than pigeonholes. Then, when you place the pigeons into the pigeonholes, when you place pigeons into pigeonholes, at least 2 pigeons will have to share a pigeonhole. At least 2 pigeons will have to share a pigeonhole. So let's take a simple example of this. You have 8 friends. 8 friends. Okay. I claim that at least 2 of these 8 friends will be born on the same day of the week. At least 2 are born on the same day of the week. And now let's see the pigeonhole principle in action to prove this. Okay, and whenever you use pigeonhole to prove anything, okay, you have to first identify the pigeonholes. So I'm going to define, and you can think of them as bins. So I'm going to define a bin. I'm going to define 7 bins. Okay, 4, 5, 6, 7. 1 for each day of the week. So you have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. I guess I drew 8. Okay, so now I have 7 bins. Okay, and each of my friends is born on some day of the week. So I'll think of them as pigeons, and I'll place each friend into the bin corresponding to the day of the week they're born. But I have only 7 pigeonholes and 8 pigeons. So at least 2 of them will have to occupy one of the bins. Okay, so which bin are they occupying? Whatever it is, I don't care. Maybe they're both, maybe I have 2 in here. So those 2 are born on a Thursday. End of proof. Okay. Now, let me ask another question. Exercise. Okay. So, exercise 1. How many friends do you need in order to ensure? So, how many friends to ensure 2 born on the same month? Okay. How many friends do you need to ensure that 2 are born on the same month? So pause the video and, try to figure this out. Okay, if you're coming back and you said 13, bingo. The pigeonholes are the months. The friends are the pigeons. You need more pigeons than pigeonholes. So you need more than 12 friends, i.e. 13. Okay, exercise number 2. Okay, how many friends to ensure that 2 are born on January? In January. Okay, now you want to ensure 2 are born in January. How many friends do you need? Pause the video. Think about this. Okay, 1, 2. Now, if you're coming back just for the ride and you said 13, no. Okay, if you said 14, no. I hope you didn't say 14. I hope you didn't say 15. I hope you didn't say 16. I hope you didn't say any number. Okay, even infinity won't work. Okay, you can have infinitely many friends, but you cannot guarantee that 2 will be born in January. Okay, because they could all be born in February. And so it's important to understand the distinction between these two claims. In the first problem, you just want to ensure that two are born on the same month, but we're not specifying which month. In the second problem, we're specifying that we want to ensure that two are born in January. That's very different. You can't really use the pigeonhole. In fact, you cannot guarantee that. You can have any number of friends and they're all born in February. Okay, so those are some simple examples where the pigeonhole principle can be used. Okay, now let's do some deep examples. Social twins. Okay, so social twins. Take any social network, for example, Facebook. So any social network. Okay, billion people, and all the friendships are arranged in a very, very complex way. Okay, so it's any social network, whatever. Okay. Now, different people have different numbers of friends. Okay. But I claim that there must be two people with the same number of friends. Even in a billion node network with very complex friendship relationships, there must be two people with the same number of friends. There must be. Okay. This is actually just a statement about graphs. Okay. In any graph. Okay. So a social network is a graph, and the friendship relationship defines the links, and the number of friends is just your degree. So in any graph, okay, there are at least two vertices with the same degree. So, two people who have exactly the same number of friends, we call them social twins. We could call two vertices with the same degree twins if you want. Now, let me be very, very clear. I'm not saying that there are two people with approximately the same number of friends. I'm saying there are two people with exactly the same number of friends. It could be 4,003,092. Okay? And there might be two people with, that exact number of friends. Okay? Exactly. That's amazing. It's guaranteed that there are at least two social twins in any social network. Two people with the same number of friends. Okay, but now I'll prove that. We're going to prove that with the pigeonhole. Okay, but let's first take an example of this. So let's construct any old graph you want. So V1, V2, to illustrate the idea behind the proof. V3, V4, let's say V5. And they're linked in some strange way, whatever you want. Okay, so here. And let's put a link here even. Okay. And a link even here. Now complicated. Okay. So, each vertex has a certain degree. So what are the possible degrees in such a graph? Well, in theory, since I have 5 vertices, in theory you could have a degree of 0. So that person has no friends. You could have a degree of 1. I have 5 vertices. You could have a degree of 2. You could have a degree of 3. You could have a degree of 4. Okay. Can you have a degree of 5? So let's think about it. There are only 5 vertices. So if I'm a person in this network, I can only have 4 other friends. So my degree can be at most 4. So I cannot have a degree of 5. Okay. Now, actually, I've defined some bins. Think of those as the pigeonholes. And I'm going to view the vertices as pigeons. Okay. And I'm going to place a vertex into the bin that corresponds to their degree. So in this case, V1 has degree 3. So I'm going to put V1 in here. V1. Okay. V2 has degree 1, 2, 3, 4. So V2 has degree 4. Okay. V3 has degree 3. So this is V3. Okay. V4 has degree 4. So V4. Okay. And V5 has degree 1, 2, 3, 4. So V5. So in this example of a graph, I see that there are lots of social twins. V1 and V3, V2 and V4, V2 and V5, V4 and V5. Lots of social twins. Okay. This is just an example of a graph where there are social twins. You can try to construct a graph where there are no social twins and you will fail. So now let's prove it. So proof. Okay, so let's prove this theorem in general. Proof. Wow. And Facebook, there are two people with exactly the same number of friends. Okay, so, let's consider a graph with n vertices. And there are two cases. So case one, okay, nobody has degree 0. So everybody has at least one friend. Okay, so every degree is at least 1. And case 2, okay, somebody has degree 0. Someone, it could be more than one person, but someone has degree 0. Okay, so just like I drew with that example graph, let's see what are the possible degrees for people in this network in case 1, okay, in this graph. So the smallest degree is 1, okay, then I can have degree 2, then I can have degree 3, and so on, 4, and so on, okay? And what is the highest degree that I can have? Well, let's think about this. So I'm a person in this network, and the network has n vertices, so there are n minus 1 other people, and the most friends I can have are all n minus 1 of them, so the maximum degree is n minus 1. Ah, interesting. So now I'm going to put every person into the bin corresponding to their degree. But look, there are n vertices. There are n people I have to put. Okay? And there are only 1, 2, 3, up to n minus 1 bins. So n vertices, n minus 1 bins. So the Pigeonhole Principle says that at least one of the bins will have to house 2 or more of the vertices. So there'll have to be at least 2 vertices in one of the bins. But those 2 vertices, because they're in the same bin, have the same degree. Okay? So those 2 vertices have the same degree. Okay? Let's look at the case where someone has degree 0. So now the minimum degree is 0. So you might think, oh, now that there's 0 degree, then there are n bins, and so my argument will fall apart. Not quite. Okay, so let's go. Well, there's degree 0, there's degree 1, there's degree 2, there's degree 3, and, dot. Let's see, what's the maximum degree that someone can have? Okay, so again, we have to think about this. Okay, so I'm a person in this network, and there's someone out there who has degree 0. So no friends. Okay, so now I'm thinking, how many people in the worst case, in the maximum case, can I have as friends? Well, there's me, there's the person who has no friends, okay? And then how many other people are there? There are n minus 2 other people to make a total of n. So I can have as friends at most those n minus 2 people, because this other loner has degree 0. Okay? So the maximum degree that someone can have in such a network where someone has degree 0 is not n minus 1, but n minus 2. So the maximum is n minus 2. And again, we're going to place everyone in the bins corresponding to their degree. But again, there are only n minus 1 degrees. Okay. And I have n people to place, n vertices to place. So at least 2 have to be in the same bin. So in both cases, you have more vertices than bins. Okay. So that means some bin has 2 or more people. Some bin has 2 or more vertices, and those 2 vertices have the same degree. Those 2 have the same degree. Very interesting. Okay, done. End of proof. In any social network like Facebook, there exist social twins. At least 2 people will have exactly, and we don't mean plus or minus 1, we mean exactly the same number of friends. Isn't that interesting? Oh, okay, it's interesting. All right. Now I want to point out something about this proof, and this is linking to the non-constructive proofs. The showing the 4-year-old, that there's a cat in the picture without actually telling the 4-year-old where to find the cat. Okay? So you might ask me at the end of this proof, okay, so you've proved to me that 2 or more people are social twins. They have exactly the same degree. They have exactly the same number of friends. Who are they? Don't know. What is their degree? How many friends do they have? Don't know. And that's the beauty of this kind of proof. Well, some people will say it's a flaw. It doesn't tell us anything about who those people are, about what's their degree. Okay? It just tells us they exist. without showing us in any way how to find them, who they are. So it's a non-constructive proof. It doesn't identify the two people who have the same degree. It just says they exist. Okay. So let's do another example, another very deep example. So let me erase. We'll be right back to do this other deep example. Okay, so let's talk about the $100 challenge problem that we had from the first lecture. So $100 challenge. Okay, remember what it was about. It was about finding matching subsets. Find subsets with matching sums. Okay. So let me remind you what the problem was. There are 100 numbers, x1, x2, x3, up to x100. And each of these were 27 digits numbers. So they're very big numbers. Okay. And the goal is to find two subsets, for example, x1 and x2, and then another subset could be x11 and x100, or, they could be different size subsets or whatever. So find me two subsets which have matching sums. Okay, interesting. And, I gave you this problem and I said, I'm going to put $100 on it. And then you might have thought, well, this guy's willing to give away $100. Maybe it's a wild goose chase. Maybe he's just, tricking us, evil professor that he is, and he's going to focus us on this problem, and there's no way to find these subsets. In other words, maybe there are no two matching subsets. So we'll spend hours and hours and millennia, and we wouldn't be able to solve the problem. So just like the 4-year-old who said, Dad, are you sure there's a cat in this picture, and I have to prove it to the 4-year-old? Okay, you should ask the same question of me. You say, well, are you sure that this problem is solvable? Is this problem solvable? And now I will prove to you, that this problem is solvable. And then you say, oh, wow, how are you going to do that? Are you going to show us the solution? No, that's the beauty of the proof. I'm going to prove to you that this problem is solvable without in any way giving you any hint whatsoever at what the solution is, what the subsets are, how to get the subsets. Okay? Just like I was challenged by the 4-year-old to prove that the cat exists in the picture without showing where the cat is, I'm going to show you that this problem is solvable. So, not only am I going to show you that the problem is solvable, I'm going to show you that the problem is solvable no matter what the choices you made for the numbers in the subset. For the numbers in the set. Okay. So, problem is solvable no matter what x1 up to x100 are, as long as, they are numbers that are not larger than 27-digit numbers. So they're all 27-digit numbers. Okay, so here's the proof. Okay, and it's a non-constructive proof. That's why you'll have no idea how to get them or what the subsets are from this proof, but it will be without any doubt a proof that's convincing you that the problem is solvable. So, let's think about a subset. Think about a subset. So a subset is, some subset of numbers like x1, x2, x3. And let's think about the sum of that subset. And its sum. Okay. So the maximum possible sum equals what? Well, the maximum possible sum is when the subset contains all the numbers. So the maximum possible sum is x1. They're all positive numbers. So it's x1 plus x2 plus x100. That's the maximum possible sum. Okay. And any 27-digit number is less than 10 to the 27, just like any 2-digit number is less than 10 to the 2, which is 100. So any 27-digit number is less than 10 to the 27. So xi is less than 10 to the 27 because they're 27-digit numbers. So this maximum possible sum is less than 10 to the 27 times 100. Okay, times 100 because there are 100 numbers and they're each at most 10 to the 27. So this is equal to 10 to the 29. So the maximum possible sum is 10 to the 29. So let's list out all the possible sums. And if we ignore the empty subset, then all the possible sums, well, even 1 is not possible because they're all 27-digit numbers. But let me even start at 1. So all the possible sums are 1, 2, 3, 4, 5, and so on, all the way to 10 to the 29. It's the maximum possible sum. And if I listed this out, it would take me a long time. Okay. But what have I done? I've created a bin for every possible sum that a subset could sum to. Okay. There are no other possible sums. So there are 10 to the 29 bins here that correspond to subsets. So I'm going to think of these as bins. Okay. Now, those bins are going to play the role of my pigeonholes. Okay. I'm going to apply the pigeonhole principle. So I need to tell you, what are my pigeons? So let's consider a subset. For example, x1, x2, x3. x1, x2, x3. That's a possible subset. It's going to have some sum. So there's going to be some sum. Okay, and the sum might be, whatever it is. Let's say, 19, billion, trillion, or something like that. Okay, so this sum, okay, can be computed. And then once I compute this sum, I can find the bin that corresponds to that sum, and I can place this subset in the corresponding bin. So place subset into bin for its sum. Okay, very nice. Okay, so, well, if I wanted to do a lot of work and accomplish nothing, I consider all possible subsets, okay, and I place each subset into its corresponding bin. When I do this for all possible subsets, so the subsets will occupy bins, and the subsets are going to be my pigeons. Okay, so the subsets, all the possible subsets are my pigeons. Okay. Well, how many possible subsets are there? And we think back to the previous lecture. The number of possible subsets of a 100 element set is 2 to the 100. So there are 2 to the power 100 possible subsets. But since I'm excluding the sum of 0, I'm excluding the empty subset. So there's 2 to the 100 minus 1 possible subsets. Okay, the 1 being the empty subset. And this number, if we compute it, is approximately equal to 1.3 times 10 to the 30, which is strictly bigger than 10 to the 29. In fact, it's about 10 times bigger than 10 to the 29. What does that mean? It means that I have more subsets than bins into which I can place them. I have more pigeons than pigeonholes. What does that mean? The pigeonhole principle says that at least one of these bins will contain 2 or more subsets. So this means that at least one bin contains 2 or more subsets. So let's examine those 2 subsets that are in the same bin. Well, how did those 2 subsets get put in that bin? They got put in that bin because their subset sum was equal to the number of the bin. So that means that those 2 subsets have the same sum. They are matching subsets. End of proof. Indeed, look at that. So I have proved that there exist matching subsets without showing you in any way whatsoever how to get them. Miracle! Okay, I can show you that something exists. Okay, I can show you that a solution to this problem exists without telling you in any way how to get the solution, how to find the solution. And indeed, one of the mentors for this class has actually solved the problem and verified that that they can find 2 matching subsets. Fortunately for me, my $100 is still intact. Okay, because it's only open to students of the class, not mentors. Those guys have become professionals. So, but that's also fortunately for you. It means that the $100 is still up for grabs. So maybe you are re-energized now because you know that the solution exists. So go and find it. Okay. So what have we done? So the last lecture and this have been on counting. Counting is very important when it comes to sort of analyzing algorithms, especially brute force algorithms that do everything in every possible way. Okay. Now, so we discussed basic tools for counting, and then today we discussed slightly more advanced tools. repetitions in sequences, and also, we discussed this extension of the sum rule to when the sets can overlap. Okay, good. And we also see here now that counting, or a very simple counting principle, the pigeonhole principle, is not only useful for counting, but useful for proving deep things, the existence of deep things. And later, we will use the pigeonhole principle to prove the existence of problems that cannot be solved on certain kinds of computers, okay, which then inspires us to seek more complex computers. And we'll keep playing that game until we get to a model of the actual digital computer that we currently have. Well, actually, we'll get to a model that's even more powerful than the digital computers that we currently have. Okay, so just a little appetizer to show you where counting will play some role when we come to the theory of computing. Okay, but having said all that, counting is very important. It can be hard to count certain things, but it's very interesting and a very beautiful subject. Okay, and so with that, read the chapters carefully, and I am checking out.